Hi everybody, I'm going to go over reductive amination in this video. So we've already talked about reductive amination a little bit, but since we're heading into the amine chapter, I figured it was a good time to kind of review it, particularly because I've gotten a few questions about it lately. So just to recap what we already know, reductive amination is the synthesis of primary, secondary, or tertiary amines, and it's going to use a couple mechanisms that we're already really familiar with. But first, let's look at what we can do with it. So pretty much we're starting with a ketone or an aldehyde. This isn't going to work on anything in the carboxylic acid derivative family. So ketone or aldehyde starting material, and then you just need an amine. Okay, so you can put pretty much anything that you want on that amine. Generally, alkylamines are going to work a little bit better than like an arylamine, but that's just because the alkylamines are going to be better nucleophiles than something that has resonance into a benzene ring, for instance. But you can do that with like an aniline group too. So anyways, we need an amine. You can use ammonia. You can use primary amine, secondary amine. Cannot use tertiary amine, so keep that in mind. But we are able to synthesize all the different types of amines through this process. So all that you need is you need your amine. Generally, you're going to have some kind of acid catalyst there. That's just going to help that mechanism a little bit, as we'll see in a second. And probably the most important part of this is our sodium cyanoborohydride. Okay, pretty much the only thing that this is used for is reductive amination. So it's a really, really good way to kind of identify when it is happening, because it's really not used for anything else. So NaBH3CN, that is sodium cyanoborohydride. Okay, the important thing about that is that it does not react with ketones or aldehydes. Okay, because that's really important, because if we just threw in something like sodium borohydride or lithium aluminum hydride, we would just be reducing our ketone or aldehyde before we even got anywhere else. So once you're at the alcohol, it's done. You can't do anything. So it's only going to react with the aminium ion that we're going to form. Okay, so it's definitely a less reactive version of a hydride source. So it's not as reactive as sodium borohydride. Can't react with ketones, can't react with aldehydes. We're only going to really see it reacting with the aminium ion that we form. And this is a kind of like one of the premier ways of making amines. And you'll see this a ton in the literature. Like, this is a very highly used reaction to synthesize amine products. So let's go ahead and take a look at the mechanism here. So the thing I want you to keep in mind for this mechanism is think about it as, first, we're going to do an amine formation, or like form an aminium ion. And then plus a hydride reduction. Okay, so that hydride reduction, it's not going to be any of the tricky ones. It's just going to be like the simple carbonyl addition type mechanism. So let's go ahead and start with the formation of the aminium ion. So I'm just going to show this on a nice simple molecule. We're just going to use acetone and dimethylamine. Okay, we're going to add some acid, and then we've got our sodium cyanoborohydride. So that sodium cyanoborohydride is really just going to sit around until we are at the end of the mechanism, and that's when it's actually going to come into play. But before that, it's pretty much just sitting there. So just like any of the imine or enamine formation steps, we are in acid right now. So the first step is going to be protonating our carbonyl there. Okay, so we can protonate there. That makes it a really good electrophile. so that our nucleophile of our amine can now come in. Okay, so then we can end up getting to this intermediate. So now we need to do a few proton transfers because we want to get rid of that OH as water. So we are going to need to protonate that, but we also need to deprotonate our nitrogen. So I'm going to go ahead and use more of that amine as my base. Okay, so then I get to a neutral molecule here. Now I can go ahead and protonate my OH, and I can just use the acid that I just made. Okay, so now I have that water as a good leaving group. So now I can reform, well, not reform, I didn't have it in the first place, but I can form that carbon nitrogen double bond and kick off our water. Okay, so again, this mechanism is just the same as the imine, enamine. It follows a lot of the same patterns that the acetal mechanism does. And once we get to our iminium ion here, that's when we're actually going to see the sodium cyanoborohydride take action. Okay, so this is going to be our irreversible step. So until now, all of this is kind of fluctuating, right? We've got a lot of acid-base action going on here. That's all going to be reversible in this case. The only thing that's not reversible is going to be this final step where we have our sodium cyanoborohydride come in. Okay, just a less reactive form of like a sodium borohydride. So that's going to come in, move the electrons up onto the nitrogen. So again, just the same as a regular carbonyl addition type reaction. And that's going to get us to our amine. Okay, so we've formed a new CH bond and a new CN bond. Okay, so we've made two different bonds here to make that final amine. Okay, so that's the mechanism. It's going to be very consistent for a primary amine, for NH3. All of those are going to pretty much work the same way. Let's look a little bit at the retrosynthesis of this in terms of how we would break it down into the carbonyl and the amine. Okay, so if we're just looking at, let's look at this secondary amine here. Okay, so this is a secondary amine. Let me get that little loop off. So essentially what we're looking at is we are looking at being able to form any CN bond that also has a CH bond on that same carbon, okay? So for instance, we've got two of those options here. We've got this one and that one. I could make either of those bonds with reductive amination. Okay, I've got an H there, I've got 3 H's over here, so I've got plenty of options. So let's look at some of these. We're going to go ahead and do these in 2 different colors. Okay, so if we take the methyl and we're going to make that CN bond. So that means I need to add another H to get my nitrogen to be neutral to start. And then that other carbon is going to be my carbonyl. So in this case, if you take away one of these H's, you're left with 2 H's, so that's going to be formaldehyde. Okay, so we've got these two things together with sodium cyanoborohydride and some acid are going to get to that secondary amine. So if we wanted to go the other way, so if we wanted to make this carbon nitrogen bond and that CH bond, then we're going to be able to work from a ketone in this case, okay, because this is going to be our electrophile. Nitrogen is going to be our nucleophile. And up here we had electrophile, nucleophile. Okay, so we've got our ketone because we're taking off that H and we're taking off the CN. And then we're going to have the nitrogen with a methyl group on it. And then two H's. Okay, because we always have to make sure that our nitrogen starts out neutral here. So if we want to look at a situation where we couldn't do a certain bond by reductive amination, if we look at, so let's say what we can't do. So let's look at a similar example here. So instead of a methyl, I'm going to put a tert-butyl group on there. So just something that a carbon that does not have any H's on it. So we cannot do this type of process. Okay, and as soon as you draw it out, hopefully you can realize what's wrong with this, because this is absolutely not okay. Let's get the red out. Let's not obscure the carbon. Okay, we do not want to have 5 bonds to carbon. So if you can't have an H add in, and if you don't have an H there, it's not going to work. So we can't do it on we can't do it with a quaternary type center. So we need to have at least one CH. To make it work. Okay, because keep in mind the two important parts is you're making CN bond, but also making a CH bond. So if you don't have a CH bond, you're not going to be able to do this process. All right, so that's the reductive amination reaction recap. So we will keep talking about this and keep practicing it, but hopefully this kind of gets some things clarified up. All righty, I will talk to you all later and let me know if you have any questions.